Hello again, my dear students, and welcome to the Informatics 2 class. We're going to start lesson number 10 now, and this lesson talks about two-dimensional arrays. In this presentation, we're going to introduce the concept of two-dimensional arrays, how to declare and use two-dimensional arrays in C, how to pass arrays as arguments or parameters to functions and how to access them from these functions. And what is the relationship between arrays and pointers? After that, we're going to talk about a very important topic called dynamic memory allocation. Okay, let's start with the concept of two-dimensional arrays. The two-dimensional array is simply a table where each cell has two addresses, a row and a column. So basically, it's a table like this with rows and columns. Okay, so this determines the rows. This determines the columns. Okay, and all I need, as a matter of fact, is a pointer which points to the first entry in this. So this is a 2D array, if you like. The way to address an element in a two-dimensional array, A, is simply by determining the row and column. So to access, let's say, any entry, this entry in here in the array, I would like to determine the row to which this element belongs and the column. So I would say something like, in mathematics, A, assuming that the name of this array is A, of I and J, and this means row I, column J. However, in C, we don't write it this way, but rather we specify it like this, A of I and J, square brackets, rows, columns. And here's a picture of the table we just drawn in here. So in this example, we have a 5 by 5 array defined to be of type integer, and the declaration statement would be something like this. A of square bracket 5, number of rows, square bracket 5, number of columns. Remember that in C, we always start the numbering from 0. So the first entry in the array is A of 0, 0. And the very last entry in this case will be A of 4 and 4. This matrix, two-dimensional matrix, is actually presented in rows and columns like that. Going to any entry within the array will be simply by identifying the row and the column to which this entry or this element belongs. The declaration in C looks like this. Integer, and we're assuming that the data type of entries in this array is of type integer. And then the name of the array, and then between square brackets, individual brackets for each entry, defining the number of rows and number of columns. So in this example, I have 5 rows and 5 columns. Well, sometimes I could initialize the matrix or the two-dimensional array as I define it. And we do this a lot in C, actually, when I say something like integer x equals to 10. I'm defining x, declaring x to be a variable of type integer, and I'm initializing this variable to be 10. So the value 10 is initialized in this variable. We do this a lot in C. In the same way, we can define an array and initialize its entries. The initialization goes between braces like this. So I say integer A of 5 and 5, 5 rows, 5 columns, brace, end brace. And then between separate braces, I put the entries of each row consecutively. So this is the first row, second row, third row, up to the 5th row. So the matrix in here is something like this. A equals something like this. 1, 0, 1, 0, 0, and then I have zeros like this, and a 1, 0, 0, 1, 0, 0, and so forth. So this is just an initialization step. And remember that in the initialization, I have a brace, closing brace for the entire matrix, and then braces around every row within the matrix. It's very simple, straightforward. How to access now entries or elements in this array? Well, in C, the two-dimensional array is really a one-dimensional array, where each element is actually stored in the memory, in a vector memory like this, because our memory actually is one-dimensional. So the entries in here are actually what represent the array. So A is something like this, and I'm going to reserve, once I say integer A of 5 and 5, I'm reserving 25 consecutive locations of type integer, 4 bytes each, in the memory. To access an element, we write in C, we write something like A of I and J, referring to the element at the ith row, jth column, again starting from 0. So physically, this entry is at row I plus 1, j plus 1, physically, because we start from 0. So that's the correct way of writing it in C, square bracket, row, column. And we didn't do this, actually. This is the way we write it, or we used to write it in the math class. However, in C, we write it this way. So for you to remember this. Elements are stored by rows. Again, in this memory, I don't have a two-dimensional memory, but rather each location in here actually is 1 byte. So to reserve a location for memory, I would need to reserve 25 consecutive locations in the memory. Each location consists of 4 bytes in this case. Of course, it depends upon the type of the memory of the array we're defining. So for this particular case, for the 5 by 5 array A of type integer, what I have is actually a pointer named A, pointing to the first entry in this block, in this vector of memory, okay, 25 consecutive locations. And what I have in the first location, I have the first entry, second entry in the first row, third entry in the first row. So the first row goes up to this point, and then right after that comes the second row. All entries in that row, third row, fourth row, and fifth row as it goes down. So basically, the physical address of any entry in this array is actually located at this address in the memory. So it's located at I times number of columns plus j. So that's how far deep from this location is my ith, and jth element in the array. So for example, if I go here, this is row number 0, column number 0. So A of 0, 0 is actually at A of 0 times 5, number of columns, plus 0, which comes to 0 in this case, so it's in here. However, if I go to A of, let's say, 3 and 3, which is the third row, third column, logically starting from zeros, then practically I already have 3 rows ahead of this one, right? And in each one of these rows, I have 5 entries. So basically, before this, I have 3 rows that are already saved in there. Each one of them contain 5 entries. So that's 15 plus 3. So that's where actually my entry is located. A very simple calculation, and we can always refer to it using the square bracket like this, or using this notation as well. Both works. Okay? We can write a simple macro at the beginning of our program to indicate that. Okay, now how to pass arrays to functions? Well, we write functions a lot in C, and we would like to access arrays defined somewhere else for some sort of calculations based on which we're going to make some results. Well, if a 2D array is to be passed to a function, then the parameter declaration of the function first must include the number of columns. Well, basically, we're talking about pointers in here. Then all I need to know is how far deep in this memory my array is. Okay, so in that case, all I care about is the one row. How many entries are there in the one row? Because the next is the same copy of this one, and if I have this pointer, I can go wherever I like. So what's important is actually the number of columns. However, the number of rows is irrelevant because I'm passing a pointer, as a matter of fact, rather than a value. Why is that? Since what is passed is a pointer to an array of rows. So when I say something like A of 5 and 5, actually, I'm defining 5 pointers, each of which pointing to a block of 5 integers. So that's basically and physically what it is when we define that in C. So let's say daytab is a matrix or a two-dimensional array that's already defined to be an array of 2 rows, 13 columns in each row. Then we can say, if I want to pass it to function if, that the argument or the parameter of this would be integer. I'm assuming the type of this is integer. Integer daytab of 2 and 13, explicitly defining number of rows, number of columns. However, I don't have to pass this. It's enough to say something like daytab, square bracket, nothing in here, okay, and 13. Because what I'm saying in here, I'm just passing pointers to entries of 13 elements each. And then I do whatever I would like to do inside that function. Or I can say something like integer, parenthesis, asterisk, daytab. And this star means a pointer. So basically, and then square bracket 13. So basically what I'm doing in here, I'm passing pointers to 13 entry each. So saying this, or the previous one where I explicitly said 2 and 13, they all mean the same. The important thing to notice in here is that number of rows is irrelevant because what I'm passing is actually a pointer rather than a value. So the parenthesis in here, which we use, this parenthesis, is actually very important. Why is that? I cannot write something like this. I cannot write function if is calling daytab of 13. I can't say this because simply this square bracket has higher precedence than this one. And that way, if I write it just like this, it would mean 13 pointers only to integers. And that's not what I want. I want set of pointers, each one of them pointing to 13 entries. Okay, let's take an example. And in this example, I would like to convert between the day number in a certain year. Let's say, what is the 101st day of year 2004? Okay, I need to say that this is the April 10th. How would I make this conversion? Let's see. Let's develop the program which performs that. Well, the 101st day of year 2004 actually covers the entire month of January, February, March. These are 91 days as we add them up, and then 10 days here. So it's the 10th of April. So for this example, I'm going to give as an input to the function the day of the year and the year number. And then the outcome will be which month and day of the month this day is actually. So basically, the conversion is very simple. I will take this and start subtracting the number of days in each month. Each time I look at the remainder after the subtraction. If it's still larger than a month, then I will go to the next month and subtract the number of days in there. Okay, and again I check, is this number still more than just 1 month? I keep subtracting till the remainder I get is something less than a month. Then in that month, which I already reached at, plus these are the number of days actually within that month. And again, I have to distinguish here between the number of days in months. Actually, we all know that number of days in each month is different from another. For example, January has 31 days. March has 31 days. April has only 30 days, and so forth. Furthermore, there is the concept of a leap year. What's a leap year? Well, that depends upon the month of February, actually. Sometimes, if the year is leap, then the number of days in February are actually 29 days. Whereas if it's a non-leap, then the number of days are only 28. And I think you all know the concept of a leap, non-leap year. Okay? So to determine exactly what is this particular day of this year, in which month and which day of the month it is, then I need to know first whether this year is a leap year or not. As you might know, the year is called leap if it is fully divisible by 400, or it is fully divisible by 4 but not divisible by 100. Okay? This is well known, actually, and you can refer to any book which talks about days and years. For that, what's important for us is that I have 2 types of years. And for that, I need to define a 2-dimensional array to where I'm going to put the number of days in each month of a leap year and the number of days in each month of a non-leap year. Okay? Basically, these 2 rows are similar except for the month of February, as I said. So January will be 31st, whether we're talking about a leap or non-leap. However, when it's leap, February is 29 to where it is only 28 when we're talking about non-leap, and then 31, and we continue up to December, which has 31 days whether leap or non-leap. Okay? For that, we're defining this 2-dimensional array. I'm calling it data of type static, and static means that this data is fixed and can't be changed during the execution of the program. And that we're going to never change, actually, these numbers in here. Okay? However, I only have 12 months in here, and actually in my declaration here, I made it of 13 columns rather than 12. I understand why this 2 refers to leap and non-leap. However, why 13? Well, remember that C always start numbering from 0. And we would like to refer to this as month number 1 rather than number 0. And that's why we inserted a 0 in here to indicate index number 0. And that's just to make life a little easier when we refer to these numbers. So it doesn't hurt if I make this day tab consist of 13 columns rather than 12 and have the first entry 0 in here. It doesn't refer to any month. And then after that, these are the numbers, the number of days in each of the months consecutively. In the non-leap, so where I have 28, and in a leap year, 29. This says leap year. This is wrong. Okay? How does the function goes after that? Well, it's going to be of type void, month, and day. And that's what I would like to return. It takes 4 parameters, the year and day of the year. This is the input, 101, year 2004. And I would like to return the month and the day within the month. Because these values are going to be changed, actually, we're returning pointers to them rather than values. And we have talked about this. Whereas I'm not going to touch these values I'm not going to change them after I return. That's why I pass them by value. And the implementation is very simple. I'm defining two local variables here, I and leap. I is going to be used as an index within my loop, and leap is to refer to the year, whether it's a leap or non-leap year. The first thing I'm going to do is to calculate the year to see if it's leap or non-leap. And as I said, a year is called leap if it's fully divisible by 4. So year modulo 4 equals 0. And divided by 100 modulo 100 is not 0. Or the year is fully divisible by 400. So this thing is going to be either a true or false. True means 1, false means 0. And that's why the first row in this array was actually, what I'm having in the real implementation is the non-leap here and the leap down here. So this is 28 and this is 29. So if it's 0, that means wrong. Then I'm talking about the non-leap year. And if it's correct, that year's leap, I'm going to use this row. And that's why I'm going to use the variable leap as the index to the rows. Okay, and then I'm going to loop over all the year days given, the 101 in our example. And I'm going to keep repeating the process as long as the number of days left here is actually larger than a month, larger than 30 or 31 days, whatever I have in here. Okay? Each time, I'm going to subtract the number of months in whatever year is, whether leap or non-leap, from and the I, and that means the month. So I'm going to subtract 31 at the beginning, then whatever, 28 or 29, then 31 and so forth. I keep subtracting, and each time I subtract, I'm going to assign the month to the ith month, right? And the remaining number of days are actually the day of the month. But of course, if this number is still too large to fit in a month, that means we have to redo this again and keep subtracting. So basically, I'm going to keep subtracting number of days according to the matrix in here till I end up with a number in here which is less than basically 30 or so, and that's when I return. So I'm in here, I'm making two assignments in this pointer at the location pointed by this pointer for the month and for the day of the month. So that's basically how we do this, and it's very simple and straightforward. It's just a way of exercising working in two-dimensional arrays. And since we're talking about pointers, and that when I define an array, a two-dimensional array, I basically have a set of pointers pointing to rows, then why having these rows of equal size? I don't have always to have the same number of entries in each row, especially when we're talking about text, names, or something like that. Number of characters in the name could be different from one name to another. And that's why a nice way of representing that would be something like this. If I define strings or names to be of type pointer of size 4, and that means I'm having like 4 pointers. These four pointers are like these. 4 pointers, as I said. The name of them, the starting pointer is strings, okay? And there are 4 of these. On each row now, I have different number of characters, generally a string, and as we know, the string always is terminated with a null pointer. So this doesn't have to be of equal size that way, but rather they could have as many number of characters as you like and then terminated by the null. So in the example here, the first row contains 4 characters, the name Bill, /0. Gates, 1 extra character in here, more characters and more characters. So the number of characters in each row is irrelevant in this case, and all I care about is I keep reading till I encounter the null counter. And this is a very efficient way of defining two-dimensional arrays to where I have different number of columns in each entry. Okay, we're going to move on now to a very important topic that we use a lot actually in programming, especially when it comes to data structures. This is called dynamic memory allocation. Well, reserving in advance the maximum number of entries in an array could be actually of some sort of a problem. Why is that? When I say something like A of 5 and 5, and I'm referring to the same example we had before, let's say of type integer, I'm reserving ahead of time 25 locations in the memory, separated in 5 rows, 5 columns each. Okay? Now, during the execution, I might realize that I will need much less than this number of elements. I only going to use something like 10 of these 25. So what's going to happen? Well, nothing actually in terms of the memory. You have reserved 25 consecutive locations in the memory. Now, in the middle of the execution, you realize that you're not going to use them. Okay, 15 of them are wasted. So this is a waste of memory. Worse yet, I might realize during the execution that I need more than just 25 for whatever reason. And this is typical in real applications. I mean, what happens if you, let's say, buy a bookshelf, okay? And you ask your dad to buy one for you, and he asks right away, how big would you like it? Because that makes difference in terms of money you're going to pay for it. So a 2-shelf kind of library, would that be enough for you? Okay, let's buy it. I paid $100 for that. I realize in the middle of the day, okay, that I'm not using the whole thing. I'm only using half of a shelf. Well, you have wasted like 1.5 of the shelf. Dad is going to start shouting on you. I could have paid $20, $30 instead of the $100. I don't need that much of space. Well, this is a problem, Dad. Yes, we could have saved some money. Well, the other scenario, you paid the $100, okay, and you started collecting papers and books and all of that. Your shelf is stuck with books. There's no place to put your books on. And you didn't know this ahead of time. At the beginning of the year, you thought the 2 shelves are going to be enough. Well, they're not. What you're going to do? You're stuck. Okay? So in the middle of the execution, you cannot change the static declaration. You reserve 25 locations. You either use them all, okay, or you're wasting space in the memory, or if you need more, there's no chance, no way that you can save more elements, more data into this block. And that's why, instead of doing this, we will reserve memory on demand. Well, how to do that? Well, in C, it's very simple. And we're going to use a set of functions that are very efficient in utilizing the memory. First, static allocation declared while you write the code, and their space exists as long as your program runs. That is, this is a static declaration, static allocation. At the beginning of your program, up there, right before you start doing anything, you declare your variables. One of them is your storage area for the array, okay? And now, during the compilation step and linking step, this location is going to be reserved for you once you run your program. You can't change the size you're allocating after that. This location is going to stay reserved for you as long as your program is running. Once you exit your program, this space is going to be freed. The running environment, and that's the operating system if you like, is responsible for allocating and freeing the space. So once you run your program, the operating system is going to look at the declarations you have. It's going to go to the memory, somewhere in the memory, suitable for this size, and it's going to reserve the appropriate size for you. That space is going to be reserved for you. Nobody else can use it till you exit. Once you exit your program, again, the operating system is going to take control to free that space and make it available for other programs or other users. Okay, so for you as a programmer, you don't have to worry about where to allocate the memory and when to free it, because that's done automatically. However, as I said, you cannot, in the middle of execution, you cannot change the size you're allocating in here. Dynamic, on the other hand, the space is created and may be destroyed during execution. So at any time, in the middle of executing my program, I can allocate no memory space for my variables, or I can destroy or free existing locations or already reserved locations for my variables in the middle of the execution. I do that myself as a programmer rather than depending on the environment or the operating system. It's accessible only through pointers, and that's a fact in C. If you allocate memory this way, actually, you need to always create a pointer to point to that location. How to do it? The programmer has to explicitly allocate the memory, and once the programmer is done with this space, the programmer has to free that space. Otherwise, it's going to stay reserved, and the operating system is not going to free it for other programs or for other users. And that's why it's your responsibility as a programmer to free any dynamically allocated space in your program before you exit your program, and once you're through or done with that space. Okay, so bigger responsibility on the programmer, but lots of flexibility because you can reserve anytime you like and you can deallocate whenever you're done with that. So before using the value of a pointer, we must either assign it to null or create a dynamic variable to which it points. So I first create then a pointer that's going to point to a storage area. How big that storage area? We're going to allocate it later on. So first, you're going to create a pointer, okay, and make it point to null, if you like. And then after that, once you reserve a space in the memory, you're going to make that pointer pointing to this block. And then after that, you can access any entry or any location within this space using this pointer, normal pointer accessing. So to create and destroy dynamic variables, the following functions are used. To reserve memory or to allocate memory, we use the function called malloc for memory allocation. So malloc takes basically one argument. It says malloc, and in here, the number of bytes you want to reserve. And always we refer to number of bytes. Okay? By default, malloc returns a pointer to whatever reserved in here. Okay? And that, by default, that pointer is of type void. However, it depends, of course, upon the type you would like to refer to that block of memory you already reserved. So basically, I could cast it with any type you like. Let's say of type integer. So make this, whatever you reserve, to be of type integer. Okay? So I say something like x equals asterisk integer between brackets malloc whatever number of bytes. Okay? So malloc integer number of bytes. In this example, I'm saying that I'm reserving number of integers. This, as a result, allocates the specified number of bytes, and they're now going to be assigned to whatever pointer you have already declared. Upon successful, the malloc will return a pointer to this block of memory. However, if it fails for whatever reason, and one of the reasons simply is there is no space in the memory, then it will return null. So we use this for decision making. Like I say, if malloc whatever equals null, that means I failed to allocate the memory. Then just return maybe or do something. Otherwise, the allocation was successful, and you can do whatever you like to do. And again, you have to remember that the operating system is not responsible for this allocated memory, as I said. And when you exit your program, that space is going to stay reserved unless you, as a programmer, free that space and make it available for others. And that's why we use the function free. And in between parentheses, I write the name of the pointer, which points to this block, actually. So that's the created. This is the pointer we're having in there. Now you're done. You're through with this. So what you need to do is to free this space by saying free between parentheses PTR. So this releases the space that was dynamically allocated for a pointer. Along with this, we use the function size of. Okay? And this size of, it tells the size of the number of bytes you would like to reserve in here. So I can say something like, let's say integer pointer x, and in the middle of my program, I say something like x equals to integer malloc 100 times size of, that's one word, size of integer. What this says in here, reserve in the memory 100 consecutive locations of type integer. So basically, what I'm reserving in here is actually 400 consecutive bytes, and make x point to that block of integers. So a block of 100 integers pointed by x. And you can refer to any one of them using this pointer now. So this returns the number of bytes allocated for a type. Static and dynamic variables. Well, let's look at the following examples to distinguish between these static and dynamic variables. When I say data type, any data type, integer, float, whatever, student 1. Well, student 1 is a local variable within this function main, okay? And a memory of this size has been allocated for it. This is static allocation, okay? And the operating system, once you exit this program, is going to free the space in here. However, when I say something like data type pointer student 2, this only reserves a pointer called student 2, but it does not actually allocate any space for the data physically to be allocated in there. Only when I say something like student 2 equals malloc size of data type, and that's when I reserve physically in the memory a block of data which is this big, pointed by student 2. In this case, this is called dynamic allocation. I have to free this space before I exit the program. Otherwise, it's going to stay reserved after the exit. And I will have a memory leak in that case. So student 1, I didn't have to free the space because it's done automatically for me. To where in here, I have to do it explicitly. Upon exit, space for student 1 is automatically freed, to whereas for student 2, it will not be freed, and you have to do it explicitly. Explicit free space is necessary to avoid memory leaks, and this is very important. Anytime you dynamically allocate space, remember to free it before you exit. And finally, properties and limitations of array representations. Well, array representations are contiguous, and that means consecutive locations in the memory, like this. So when you say A of 10 and 10, you're reserving 100 consecutive locations, one piece, one block in the memory. Well, this is a problem sometimes because I don't have, the operating system does not have contiguous 100 locations to do that. So this is a limitation. However, I might allocate for you 100 locations here and there. but not necessarily contiguous. Okay? We're going to see how to refer to these and make successful allocations later on. But for arrays, I cannot do it unless I have physically this much of memory. So in that case, location of next element is simply calculated. Okay? The first element in here, the second element is whatever size plus 1 and so forth. Deletion and insertion of elements. When elements of an array vary in size, memory use is not efficient. When the size here is not the same, then I'm afraid I don't know how to access the different locations. Actual used space might be much less than reserved space, as I said, because you thought you're going to need 100 locations, but practically when you ran the program, you realized that you're only using 20% of that space. So that space is wasted, basically. So dynamic allocation is definitely better. That's pretty much what we would like to talk about in two-dimensional and generally multidimensional arrays, and the dynamic allocation of memories. To see more exercises and to see reference to this material, you can definitely go to the internet, to the UNINETTUNO website, click on the MidNetU project, and you're going to find lots of interesting stuff. See you later.